Okay, now I see. Okay, very good. So let's start right away with lectures. So you know that this week we had lectures 6, 7, and 8 to cover. So lecture 6 is about kinematics of constant acceleration. So last time we saw the displacement, we saw the velocity and the speed, and this time we will focus more about acceleration. So for example, just a review quiz, the graph below shows the velocity versus time for an object traveling along a straight line path in the x-axis. So let forward correspond to the plus x direction. And then we have the object, question number A, the object, let me see, so I just read the good one. The object reverses its direction of travel at time B. So this is the velocity. This is the velocity. Is the object reversing its direction at travel at time B? No, it's essentially false, this thing, right? And then the object returned to its starting position at time C. No, because again, here we have the velocity. So we cannot really say, we say that at time C and time A, the velocity is going to be equal to 0, but it doesn't say that it goes back. Actually, it said that it goes forward in the x direction. So it's false. When is the object at rest, even if momentarily? And this we already answered to that, is in point A and in point C, because we see that the velocity here is essentially 0. And which of the following best describing, which of the following best describe the object speed? So increasing during AB, max at the position B, and decreasing during BC. Indeed, we see that between A and B, here we have the time going in this direction. Between A and B, the velocity increases, gets to its maximum and B. And then after that, we see that while it passes the time, the velocity go from the position B back to 0. So it decreases. Which of the following best describe the object acceleration? So the acceleration is positive during AB, 0 at B, and negative during BC. How can we say that? So the fact that the velocity is increasing during AB is because we have a positive, so means an acceleration in the same direction during AB. In B is 0. We know that when we have a constant velocity means that we don't have acceleration, right? So if we don't have acceleration, the velocity is constant and is 0. And then instead we see that the velocity between B and C is decreasing because it's going from VB, the velocity in the point B, towards 0. So again, from the maximum, so of the acceleration to the 0. So here we have again that is negative during BC, the acceleration, because it's going in the opposite direction of the velocity. Okay, so I don't know if we want to review also this position quiz. So here we have positions versus time, which is for an object that is traveling along a straight line path. So here we have the origin, it starts at the origin, time A, at point A. Then while the time passes by, we go to B, and then it goes back to the point C. So the object reverses its direction of travel at time B. Yes, so we see that it goes in this direction, it gets to XB, let's call it, and then while the time passes by, it goes back toward the origin point. So yes, it reverses its direction. The object returned to its starting position at time C. Is true because at time C, the position X is 0. Here in this axis is 0, exactly as it was in position A. When is the object at rest? Even if only momentarily. The object is at rest in the point B because it's when it's changing its position, its direction from one direction to the opposite direction. Which of the following best describe the object speed? Decreasing during AB, 0 B, and increasing during BC. And which of the following best describe the object acceleration? The object acceleration is negative at all times. So you will see better this concept in lecture number 8. So it will be way more understandable when you get there. In lecture number 7, sorry. So here, instead, in this lecture, we want to focus on the constant acceleration. And so we have that the average acceleration is delta V over delta T. So if the acceleration V initial and V final are the same, then we can speak about the constant acceleration. So the acceleration and the acceleration in this case maintains a constant value over time. So the acceleration, when we define average acceleration, we say that is defined as V final minus by V initial over delta T. But we can also rearrange this equation and find final velocity as a function of the initial velocity, the constant acceleration, where we just indicate with A. So there's not going to be essentially A final and A initial, because A final and A initial are going to be the same, right? So we just indicate as A. So the final velocity is going to be equal to the initial velocity plus A, the acceleration, multiplied by delta T, where delta T is the time elapsed from the initial and the final time. If the initial time is 0, and normally we start to count the time in 0, then we can even simplify even more this equation, saying that the velocity is equal at a certain time t is equal to the initial velocity v naught plus acceleration multiplied by t. This is very important equation, and you should memorize this equation because you are going to see it all the time. So this is the equation that we just said. So if we want to calculate, instead of the velocity at that particular time, if we want to calculate the position at that precise time, then the position is equal to the initial position x naught, which might be the origin, as we see in the example of before. So in that case will be 0, but it could be also something positive or something negative, right? And then, so x naught plus v naught multiplied by t plus 1/2 at squared. And this is the second equation of kinematics with constant acceleration. Constant acceleration in the sense that the acceleration never changes, and indeed is always indicated with a. We don't have as for x and b in a naught and a final. It's only a constant. Okay. So if, again, we have a constant acceleration, we also can have put these equations together and find, for example, the velocity, the final velocity, as a function of the acceleration and also the position. So instead of the time, like this equation up here, when you know the acceleration, the time, and the initial velocity, here you don't use the time, because for certain problems, you don't know the time, but instead what you know is the initial velocity and you know the displacement. So from the x final to minus initial position. So if you know the displacement, this is the equation that you want to use. And indeed is v squared is equal to v naught squared plus 2 times the acceleration delta x. Well, you need to recall that delta x is always x final minus x initial. Okay, then in this case, again, we can rearrange these equations and have also that delta x is equal to v plus v naught divided by 2 multiplied by t. So those are all the different way to write the same equation depending on what you have in your problems. So it's really good if you memorize all these equations, or before your midterm you have this equation in a very convenient place so that you can check them out, and where you are going to see, so the velocity, you can measure the final velocity if you know the initial velocity, the acceleration, and the time. And you can know the final position if you know the initial position, initial velocity, time, and acceleration. But you also have another equation that tells you the velocity in case you need the initial velocity, acceleration, and displacement. And also how is the displacement as a function of the velocity and time. And alternative formulation, again, if the acceleration is constant over the time interval delta t with t final minus t initial. In this case, the case of before is if the initial time is 0, while here, and that's why we indicated only with t, because it's only t final essentially. But if instead you have a different initial time, like in some problems you heard that at the beginning your car is going to do something, and then after 5 seconds your car is going to do something else, then you have an initial time for the second part of the problem. So you have to substitute t pretty much with delta t, where t initial in this example that I just gave you is going to be 5 seconds. So I hope it makes sense to you. And just to see if it makes sense to you, let's do a problem. So a problem that you have from your tutorial. So next time we will see if you keeping doing some problems from the tutorial or adding new problems. So this one is the tutorial 6 and is the problem number 6. And it says a toy car is constrained to move along a straight line track, defining the x-axis. So this car is starting from rest. What does it mean starting from rest? This is already a very important information about this problem. Starting from rest means that the car is with initial velocity equal to 0. So what I normally do when I start problems like this, I normally write right away these informations in a place. So in this case, we have that V naught is equal to 0. Then it starts from rest in a position which is x minus 50 meters. So here it just says x. But if you don't want to get confused, you should write x initial or x naught. Like this, you know that is the beginning, right? So in my case, I wrote it x naught is equal to minus 50 meters. And this is at t equal to 0 seconds. So, okay, this I didn't write it, but keep in mind t is equal to 0 seconds. Then the car accelerates at minus 1 meter per second square for the first 10 seconds. So again, if you go here, A in the first 10 seconds is minus 1 meter per second square. And delta t, because initial time is 0 and final time is 10 seconds, delta t from 10 seconds is equal to 10 seconds, okay? Then he said, then the car immediately changes acceleration to plus 2 meters per second square for the next 10 seconds. So if we go back here, we see that A for the next 10 seconds, so I just decided to call it A20, is going to be 2 meters per second square. And delta T20, which is the one that goes from 10 seconds to 20 seconds, is going to be 10 seconds again. Okay, then the car goes at a constant speed for the next 20 seconds. So constant speed, what does it mean constant speed? We know that when we have constant speed, that the acceleration is equal to 0. So A that gets up to 40 seconds is going to be equal to 0. And delta t at 40 seconds, we define it that is equal to 20 seconds. Okay, so now we brought down all this information which might be useful. Let's see what the problem is asking. What is the car velocity at t equal to 10, 20, and 40 seconds? So in the first part of the problem, it wants to find the velocity at 10, 20, and 40 seconds. So here, essentially, we have all the accelerations, right? Because we have the acceleration at the beginning in the first 10 seconds, which is -1 meter per second square. So here is the drawing of the acceleration versus time, -1 meter per second square. Okay, very good. Then we know that in the following 10 seconds, the acceleration becomes +2 meter per second square. So it's up here. Then what we know is that in the last 20 seconds, so for delta t that goes from 20 to 40, what we have is constant velocity, which means zero acceleration. So we just do something like that. Okay. Now it wants to know the velocity in this location at 10 seconds, at 20 seconds, and I believe at 40 seconds. So we have the equations that we saw before. Let me see the equations. Okay. So we know the velocity, we know the acceleration, we know the initial velocity, which is 0, and we know the time. So for the first case, we can use this because the time starts at 0, but after that, we can use this equation down here because time initial is different from 0. So if we go back here, V at 10 is equal to V naught plus the acceleration during that period of time multiplied by delta t. So V naught is equal to 0 plus what? Here we have a negative acceleration, mean -1 meter per second square multiplied by 10 seconds. So if we calculate this, if we make the calculation, we find that the velocity at 10 is equal to -10 meter per second. Okay, so we can just draw here the velocity goes from 0 to -10 meter per second. Very good. Then with the same method, we can calculate the velocity at 20. The velocity at 20, this time, which initial velocity are we going to use? We're going to use as initial velocity the one that we had at 10, right? So this second part here, when we have a different acceleration of +2 meters per second square, is like if we are starting the problem from 10 seconds. So we want to put, instead of V naught, instead of the initial velocity, which will be here, and it doesn't make any sense because we are already here. So for this part of the problem, you want to use this one as initial velocity. So you just put V10 as initial velocity plus A, the acceleration that we have between 10 and 20 seconds, and then delta t between 10 and 20 seconds. So here, the initial velocity, you're just going to use the one that you calculated before, -10 meter per second plus 2 meter per second square multiplied by 10 seconds. You know that seconds and seconds goes away, which makes sense because we are looking for a velocity. And so this needs to be a velocity. And indeed, we have -10 meter per second plus 20 meter per second, which is equal to 10 meter per second. Very good. So we find that the velocity between 10 and 20, right? In 20, actually. So in the last position. So here, the velocity in 20 is +10 meter per second. So essentially, I just make a straight line going up. This straight line, as you see, cross the 0. What does it mean? That at that position, the velocity is equal to 0, right? So here is equal to 0. And then it goes to +10. Then the problem is asking to calculate the velocity at 40. So the velocity at 40 seconds, again, we need to start from the initial position, and this time the initial velocity, sorry, and this time the initial velocity will be this one. So we are trying to figure it out how will look like the velocity here. So this we know is plus 10 meters per second, and we need to know how it ends here. And so in this case, we have V20 plus the acceleration at 40 that we know that is equal to 0 because we say that it's constant acceleration multiplied by delta t. Delta t this time is going to be 40 seconds. So we write 10 meters per second plus 0 that multiplies 20 seconds is equal to 10 meters per second. Now we calculated that, but could we already know that it was 10 meters per second? Yes, because it says that in this part here is constant, the velocity is constant. So it's at the beginning is 10 meters per second because we just calculated before. Here at the end, at 40 seconds, it must be 10 meters per second. Can you hear me or not? Because here I have some people that are doing a very hard work.
Yeah. Yeah, we can hear you, Monica.
Okay, I'm sorry for this. It's been cleaning the whole morning. I don't know why they keep passing through in front of my house, but okay. So this was the first part. If we go to the second part, let's see what the problem then asks. What is the car position at time 10, 20, and 40 seconds? So if we go here, again, we go to our lecture. Which one of these we can use? So we have options, but we can definitely use this one because we just calculated the velocity. We know all the delta t's and we know the acceleration. So we essentially know everything. We just need to plug the right number. So in the first 10 seconds, we have x naught plus v naught delta t in the first 10 seconds plus 1/2 the acceleration of the first 10 seconds delta t to the square. So we know that x naught was 50 meters. We wrote it up here. It was the beginning of the problem saying we start from minus 50 meters. So our position in x is minus 50 meters. So minus 50 meters plus initial velocity v naught. Oh, it's here. It's really here, this guy. It's 0 plus 1/2 1 meter squared times 10 to the second squares. So you see that here again, the second squares and the second squares goes away, which is what we want because we want a position. We are looking for a position. So the units must be only meter. You need to remove a time from the units, which is fine. So if you do the calculation, here, I'm sorry, it's a bit deleted because it goes in the next page, it comes out with minus 100 meters. So in the position at 10 seconds is minus 100 meters. Here is 10 seconds, here we are minus 100. Would it be straight as here? We know that it's not straight as here. Is the velocity that we know that is a straight curve, while remember from the beginning of the previous last week's classes, we were seeing that instead the velocity here should be, the position here should be a curve. So let's just assume that the curve is like this and not a strange one. And we assume that simply because we see that the velocity here is constantly decreasing. But if you want, you can find, as you will see in the tutorial, you can find additional points here along the path to be able to draw better this line. Okay, then here is asking the position at 20. So the position at 20, this time again, the initial position is going to be what? The position at 10, that we just calculated, which is going to be minus 100. So minus 100 plus the velocity at 20, delta t in between 20 and 40 plus 1/2, because we are, no, sorry, I jumped to the other one. I'm here, sorry. So the position at 10, the velocity at 10, delta t between 10 and 20, plus 1/2, the acceleration between 10 and 20, delta t between 10 and 20 to the square. So here we have minus 100 meters plus the velocity in that position, we know that is negative, minus 10 meter per second. The time, delta t, we know that is 10 seconds in that interval of time, plus 1/2. Here, the acceleration was positive, 2 meters per second square, multiplied by 10 seconds at the square. Again, if we make all the calculations, seconds and seconds, always check the dimensions. So seconds and seconds here goes away. Here we have second to the square, but also this second is multiplied to the square. So at the end of the day, we'd end up with minus 100 meters, minus 100 meters, plus 100 meters. So at the end of the day, we have minus 100 meters. This is the position at 20. The position at 40, we just repeat the exact same thing as we said before. This time, the initial position is going to be the one that we just calculated, x20. The velocity is going to be the velocity between 20 and 40. Delta t is going to be between the time between 20 and 40, which is 20 seconds, plus 1/2 the acceleration between 20 and 40, multiplied by, again, this 20 seconds to the square. So we have minus 100 meters plus the velocity here was 10 meters per second multiplied by 20 seconds, plus 1/2. The acceleration on this last part, remember, was the velocity was constant, so the acceleration was 0. So this part here goes away automatically. So we have minus 100 meter plus 200 meter equal to 100 meter. And this was pretty much was asked in this first part. Then for the same toy car, graph position, velocity and acceleration for the car of the following axis from t to 0 to 40 seconds. So here we kind of already done that. So I showed you for the velocity. For the position, we said it goes from minus 50 to minus 100. Then it goes again to minus 100. And I see that somebody is writing here. And then from here to 40 seconds, we see that it goes to plus 100, which is here. The problem is also asking, is there an instant time when the car is momentarily stands still? And you need to put a S where it stands still. So it stands still when the velocity is equal to 0. So when this curve crosses 0. So in the origin, essentially, but this we knew at the beginning. So it's not the one that the point that we are looking for. The point that we are looking for is this one here between 10 and 20, which is probably going to be 15. So this is the point. And if you want to see it, is also here. And we can put the point also here in the acceleration just to see where it is, where it stands. Then, is there an instant time where the car passes through the origin? If so, clearly mark this with P. So when is passing through the origin? To passes through the origin, passes through, we are speaking about the position. So what you need to do is to check in the position, the car that went from minus 50 to minus 100 and then to plus 100, there was a time when it crossed the origin, which is in the point P. And then you can put, just for information, also in the velocity and also in the acceleration, just to see where it is. But here you need to find this point P from this plot. Okay, and this was the problem. So this is essentially a problem that shows you some of the, and you can see all the rest of the tutorial. So this is just an example to see in about lecture 6. Now, were there particular questions for this part? Otherwise, we can go to lecture 7. In lecture 7, what we are going to do is the kinematics of the free fall. So you're going to understand better what is a certain type of motion. And here, let's start with the definition of the free fall. So free fall is when the only force which is acting on an object is the attractive gravitational force of a nearby planet. So object can be launched with any initial velocity, and then you only have the gravitational force of a nearby planet or our planet. So here we can consider forces that cause an object not to be in free fall. For example, is the air resistance. So every time you throw a ball up in the air, of course, it's not free fall, right? Because we always have air resistance. But we consider special cases where we ignore the air resistance. And so we can consider these cases as a free fall. Well, you know that to be in free fall, you should go to space and do what Bezos and other people are doing with in suborbital plane. So the air resistance, otherwise there is the air resistance, and this make it in a way that is no more in free fall. Or another reason why an object might not be in free fall is because there is a force from a person's hand. So if you give an initial acceleration to this object, not an initial velocity, but an initial acceleration, then you are also like, if you boost a rocket in space, you are providing an initial acceleration. So there is not only the gravity, right? Or as is written here, also propulsion from a thruster, or a contact support from a surface like ground, table, or ramp. So the acceleration is considered constant at all times. So you can use essentially the equations that you saw before. And the direction, the magnitude of this acceleration is g, gravity, and the direction is always downward, so toward the center of our planet. This acceleration is the same for all objects of all masses, okay? So the first one that did this was Galileo Galilei, that studied that. I actually saw the real thing is in Florence in the Galileo Galilei Museum, where he made all this calculation. So the magnitude of the gravity here is plus 9.80 meter per second square. Okay, and we are going to use this number all the time. So please don't put G only 10 meter per second square, because you need to use always 9.80 meter per second square. Okay. Then let me go to one of these problems. So here we are not going to consider the friction of the air. We are just going to consider this lady that throw a ball with a certain initial velocity up, and then the ball is going to come down. So again, here with the red, you can see the position of we have the acceleration. The acceleration is constant during the entire path and is all the time going downward. And that's why we call minus g. If we consider going up the positive direction, then g, the acceleration is minus g, minus 9.80, okay? If you would consider instead the y direction going down, the positive y direction going down, then in that case, you will have that the acceleration and the positive y direction are going in the same direction. And then in that case, you will have that the acceleration is positive. But it's not this case, because this case, you see yt is increasing in this direction, going up. So in this case here, let's see what we have. Let's start with the position. The position is the easiest one. Here is the hand of the lady. So the point A, the ball goes up, up, up by while the time passes by up to a certain altitude. And here at a certain position, this is going to be the max, the apex, what is called here the apex, where the velocity is equal to 0. At this point, the velocity is equal to 0. And then the ball comes back to the initial position. I mean, here it keeps going down. But in our example, let's assume that it stops in C. So in C is in the initial position as in A. So let's see let's study the motion between A and C. So here you have an initial velocity. If you notice this, the error here, the green errors of the velocity are becoming smaller and smaller until at the apex you get to 0. And why is that? Because of course you have the acceleration at all times that is decreasing our velocity. So here, remember, we have our velocity that is V naught, the initial velocity, okay, plus AT. In our case, A is minus G, so it's negative. So it's going to decrease the velocity until the velocity becomes 0. When the velocity becomes 0, what happens is that we have only the force of gravity that keeps going down, the acceleration. And so we are going to have a velocity that will start to increase, although is negative, increase again while time passes by because of the presence of the acceleration. So if we want to see the velocity, we start with the certain V naught at the beginning. We get to 0 in the same position where we have the maximum of the altitude that the ball can reach here at the top. The velocity is 0. And after that, you see the velocity changes the sign. So before it was positive, here is negative. Is negative and it gets more and more negative, okay? If we need to do instead the graph for the acceleration, we say that is constant at all times and is minus 9.80 meter per second square. So here you know exactly which value is at this point, okay? So here we have another example. I should go more faster, otherwise we cannot do it. Here we have another example when the ball is thrown from the top of the building. So the ball keeps going. When it's here, keeps going. So the velocity keeps increasing, although it's a negative velocity, right? Because still we have the acceleration that is playing a role. So if we look at here, we see 0 is the initial position. After 3 seconds, we are again here, okay, in y equal to 0. And after that, it goes down of the building. And so this is the graph of the velocity. The graph of the acceleration, we know, is going to be constant the whole time. So I don't go through this. I want to see a tutorial problem instead. So this is tutorial tutorial 7, problem number 3. We have a stone that is dropped from rest at the edge of 75-meter high cliff. Ignore here is a resistance and choose plus y direction to be upward. How much time does it take to the stone to land? So here we have 75, those are the things of the problem. We have 75 meters. Initial velocity is equal to 0, right? The stone is dropped from rest. This is the key word, from rest. So write V naught equal to 0 meter per second. We said Y initial is 75 meter, Y final is 0, right? It wants to know how much time does it take for the stone to land. The stone is land when you get at the bottom of the cliff, which is 0. So Y final is 0 meter. Initial time, we assume that is 0. The acceleration, you just draw it like this, is minus 9.80 meter per second square. So it's asking for T final. As you see here, the equation is exactly like the equation that you saw in lecture number 6. The only difference here is that instead of X, we are looking at the position along Y. So you just have to substitute X with Y, but it's essentially the same. So final, Y final is equal to Y naught plus V naught T final plus 1/2 A T final to the square. So in this case, we have 75 meter plus initial velocity, which is 0, plus 1/2 9.8 meter per second square, T final to the square. And all this needs to be equal to 0. So in this case, we have that here I forgot to put the minus. You see, there is not the minus. Well, there should be the minus because we say that Y is going in this direction, A is going in this direction. When you do the calculation, so here there should be a minus. When you do the calculation, you find out that, and this needs to be, Y final needs to be equal to 0. So you find 9.8 meter per second square times to the square equal to 150. That gives you the final equal to 3.91 seconds. So you can redo this calculation, but the calculation should be fine. I simply forgot here the minus. Then is asking in B, and you have all these solved also in the solution. What is the stone velocity at landing? The speed at landing. And so if we go here, the velocity at landing means the final velocity. The final velocity to the square is equal to the initial velocity to the square plus 2 times acceleration delta y. So in this case here, we have final velocity to the square is equal to initial velocity, which is 0, plus 2 times what? The acceleration, which is minus 9.80 meter per second square, multiplied by delta t. Delta t, which is final position minus initial position. Final position is 0 when we land to the floor, minus the initial position, minus 75. If you do the calculation, you find the square root of this number. This number, it gives plus and minus 38.34 meter per second. Now, of these two, the one positive, the one negative, we know that the one that we need to pick up is the negative velocity. Why is the negative velocity? Because we know that the velocity is going downward. Here, the velocity to get in this position, the velocity needs to be downward, right? Remember also before the motion of before was the ball was kicked up and then was coming down with the negative velocity. In this case, the motion is simply, it gets kicked down of the hill. So like this. So the velocity is going down. So must be negative because y positive goes up. Then is asking, choosing plus y to be upwarding and choose y equal to 0 ground level, graph the stone's position, velocity, and acceleration in function of time, and label your axis with a few numerical values. So if we go here, again, so here we have yt versus t. We have 0, we start at 75 meters, and we see that after 3.91 seconds, which is what we found in the first question, it lands at 0. The velocity, instead, we start from 0, and with negative velocity, we reach minus 38.3 meters per second. Of course, at the same time, 3.9 seconds, right? When the stone is landing to the floor. And if we look at the acceleration, A over T is always minus G at the time of the release until the time of landing. It never changes, a constant acceleration. So with this, I think we finished with the first two lectures. And so next time we can do the last one.
That makes a lot of sense because this finishes one-dimensional kinematics, whereas lecture 8 is 8 and 9 are just vectors. So it's like vector arithmetic, how to use vectors. Hey everyone, I know we're at the end of our time. I just wanted to remind everyone that I sent out a notice that we've made some modifications to our weekly hours. So please check this schedule before coming to our drop-in hours. There have been a number of changes. So there were enough changes that I actually made an announcement. Usually when it's a tiny little tweak, I won't bother to blast out the notice. If you would like further assistance, Julia is going to be holding 1 hour of assistance right now. So starting right at the bottom of the hour. So she'll just take a 5-minute break and then she'll come back. And then right after her, we have a number of other LAs scheduled for much of the rest of today. And to remind you, your first recitation problem set is due in La Lima tonight at 11:55 p.m. Okay. My own office hours are now moved to Tuesdays. Great. Thanks, everyone.
Another thing that I want to say, but you are free to leave if you want. I want to reply to Devin. So Devin, the acceleration is always going through our planet, right? Because it's our planet that generates the acceleration. So is always going downward. To be positive or negative depends on the y-axis. If the y-axis going to the center of our planet, then the acceleration is positive. But most of the time, because they are going in the same direction, but most of the times, y is going to be going up in the sky, not to the center of our planet, up in the sky. And if it goes up in the sky, then the acceleration is always negative. I hope it makes sense to you. Okay, that was it. Thank you. Bye.
Thank you. Thank you.
Should I just stay and wait 5 minutes or for a question?